Correlated means independent. Okay, these are independent value, no relationship at all. Independent. So the previous value, okay, does not affect the next value. But when we have autocorrelated, the next value is dependent on previous value. Okay, dependent with tendency to move in long run on either side of the mean. Okay, so if we see here, example A, stationary and uncorrelated. So this is stationary and uncorrelated. Okay, so the value varies, okay, between upper limit and lower limit. But when we have this example for B, these are stationary and autocorrelated. Okay, autocorrelated. So if it follows the previous value, so we see that this not a random variation. This one is random variation. Okay, so but if we plot the mean will be stationary. Okay, the mean will be stationary. It's about the same mean, about the same mean. We get a mean there. Okay, this is also same, the mean. Okay, the mean is the same. So but the values varies, okay, according to the previous value. They are dependent. In this case, okay, this is non-stationary. Non-stationary means process drift. Okay, process drift without any sense of stable or fixed mean. The mean is changing. Okay, we see that if the mean, if we take the mean will be like this. Okay, the mean doesn't stay at one point. It is reducing in this case. But in this case, the mean is stationary. And also here, the mean also is stationary. So this is type of variability. Okay. Okay, what are the reasons that control charting is becoming popular? Okay, what is the use of control chart? Okay, reason for having control chart. Okay, so control chart can be used as a technique to improve productivity. Okay, by having control chart, we can control or we can detect potential defects that can be produced from the process. So it's more on preventive. When we can prevent defects, okay, our productivity will increase because we don't produce bad products. Okay, so it's for defect prevention. Control chart can prevent unnecessary adjustment. Okay, sometimes when we are running a process, we see that the variability happening in the parameter or process setting. So if we understand the pattern of changes, so that will not let us to do adjustment unnecessarily. Okay, so we are guided by the information that we can interpret from control chart whether we need to adjust or not, because sometimes variability is random. Okay, so but when that is random, we don't need to do any adjustment. Okay, number 4 is control chart provide diagnostic information. Okay, we want to rectify a problem. Control chart provide diagnostic information, especially the patterns. We can get information from the variability patterns. The patterns information on the control charts give us diagnostic information. Number 5, control chart provide information about process capability. Okay, remember I mentioned earlier CP. Okay, the CP value can be obtained from control chart. Right. Okay, so in control charting, we have control limits. Control limits. So how do we decide control limit? Choice of control limit. Normally, control limit is determined as plus minus 3 sigma. Okay, plus minus 3 sigma. Okay, normally we use plus minus 3 sigma as control limit. Okay, so in control chart, you must have central line, which is normally for X. If for X bar chart, okay, for X bar chart, the central line will be double X double bar. Okay, X double bar. So we're going to have upper control limit, okay, for X bar chart. And we have, sorry, the line should be straight, because this is freehand. So it doesn't go straight as I wanted to be. So lower control limit, okay. So the distance between this value, okay, is going to be plus 3 sigma, and going down is going to be minus 3 sigma. Okay, so this is what we call the choice of control limits. Okay, so 3 sigma control limit. If we choose this plus minus 3 sigma, we're going to have probability of type 1 error of 0.0027. Okay, so this is the error that we're going to get. Error here meaning that the process might be unstable, but there is possibility of, okay, we call it false alarm. Okay, this is false alarm. This is like when you have a fire in a building, okay, you have fire system, somebody go and press the button, suddenly the bell ringing. Actually, there is no fire, so this is false alarm. So same as here, type 1 error is false alarm. When the process is stable, okay, the process is stable, but the control chart showing, okay, the point is outside control limit. So this is considered as false alarm. Stable, but okay, but data outside. So the data you observe is outside control limit. So this is false alarm, we call it. Outside control limits. Okay, CL is control limits. So actually the process is stable, but it goes to false alarm. So if I plot it this way, if I plot like this, okay. So if I have this is the center line, okay. So I may have the observed values. Let's say this is my observation values, okay. So I measure and I plot on the contour chart. Okay, over the time, I will have enough data for me to come up with, let's say, a histogram. Okay, and then I will count how many within these values, how many on this, how many of this. Okay, I can plot a histogram based on numbers of value falling within the range. So I will plot a distribution for this. Okay, so you will get something like this. So what is inside? Actually, the process is stable. Maybe a few point maybe wrongly, come outside. Okay, so there is possibility that the process is stable, but a few points will be outside. So this happen due to type 1 error. Type 1 error. If this is happening for a stable process. Okay, so if we find out there is no reason for the point to be outside, so the process is stable, so we call it false alarm. Okay, we call it false alarm. And this point that contribute to false alarm, okay, they are actually at this point. At this point. But the process is stable. It's a stable process. Okay, so how we decide this? We use 3 sigma. Okay, 3 sigma as control limit. Another way of setting a control limit is using probability limits. Okay, we can decide this line based on probability limit. So type 1 error probability is chosen directly. For example, if we want to have a probability of type 1 error of 0.1% is or 0.001. So so this which is smaller than 0.0027. Okay, so this will give us a control limit of 3.09. Okay, which is slightly bigger than this value, but this value is 3 sigma. Okay, 3 sigma we give this error 0.0027. This is statistically has been tested. This value is statistically has been tested 0.0027. But if we set our control limit at 3 point, let's say you take this point 3.09, 3.09 sigma. Okay, and also here 3.09 sigma. Of course, it is bigger than 3 sigma. Okay, so the probability of false alarm is only 0.001. Okay, so this is like 0.1%, 0.1%. Okay, another way of setting the control limit is we call it warning limit. If we take 2 sigma, so this is considered as warning limit. Okay, so we have 3, but we take 2 sigma from the center. This is called as warning limit. Sometimes it's useful to have warning limits because if observation is outside warning limit, we are more careful in the process. We take precaution, action, so that there will be no products will be outside the control limit. Okay, so that plus minus 2 sigma is known as warning limit. Okay, so remember that in control chart we have center line. Okay, center line. In this example, we have 2 sigma as a warning limit. Okay, UWL, okay, upper warning limit. Okay, 3 sigma is upper control limit. Okay, so our sigma here is based on sample average. Okay, you see the symbol here for X bar chart. We take sigma X bar. Okay, because every observation that we plotted here, these values and that we plot is average value, is X bar value. Okay, and the center line is X double bar for X bar chart. For X bar chart. Okay, any question to this point? Hello? Okay, all right. So there is sometimes we can see a pattern appearing in on control chart. Okay, example of pattern here. You see there is a pattern here. Okay, which is moving up. So this is not a normal random variation. There is something is wrong there. Okay, and also when suddenly you have a point outside here. Okay, point outside here. Don't confuse with false alarm. If there is a point here, there is assignable cause, so the process is unstable. Okay, so there will be we need to interpret this pattern, the pattern that happening on control chart, we need to interpret, okay, what actually happened. Okay. All right. How do we decide? Okay. How often that we want to collect the data, sample size and sampling frequency. Okay. When we run a process, we need to decide now. Okay. What should be the sample size and how often we want to take the sample. Okay. So this is based on what we call the average run length. Average run length is a measure. Okay. We can have ARL. We can have ARL 0, okay, for a stable process. Okay, we call it ARL note here 0 or ARL1. Okay, this is for unstable process. Okay, so one way to decide what is RL value is using this formula. ARL equal 1 over P. Okay, so P is probability any point exceed the control limit. Okay, so this also will be used to evaluate the performance of control chart. Okay, to evaluate how good is a control chart that we are using. So for a typical stable process, this ARL normally the value is 370. Okay, average run length, meaning that if we run a process, the process has no problem. On average, after we produce 370, we're going to have on average 1 false alarm. Okay, so ARL1, this is, we call this average run length when there is instability in process. So when the process is unstable, we want ARL1 to be as small as possible. Okay, so this value we want to be as large as possible. Okay, we want it as large as possible because the process is stable. As large as possible. Okay, as large as possible for stable process. Stable process means process has no problem. Because of sampling issues, okay, we may have some false alarm happening. Okay, this could happen on average after 370 runs. Okay, this has been tested and proven statistically 370. Okay, when the process is unstable, okay, so we want it for unstable process. Okay, we want this value to be as small as possible. For unstable process, the unstable process means the process is having problem. Okay, the problem might be the tool wear, it could be the tool broken, okay, create the problem to the process. How do we know the tool has broken? Because we monitor the process parameter or we measure the product that has been produced. Okay, and then we plot the value on the chart. So we know from the chart. Okay, for unstable process, okay, we want the value, okay, ARL, okay, to be as small as possible. As small as possible because we want a quick detection. Okay, so that's why we want it as small as possible. For example, when there is cutting tool has broken, we want it ARL or what we call average run length to detect immediately. Okay, sometimes it's not possible to detect when we have, for example, ARL equal to 1, meaning that it's broken and we detect immediately. Sometimes there will be a delay. Maybe we detect at ARL equal to 4 or RAL equal to 5. Mean that the broken has happened, but we measure it on the piece number 4 instead of the immediate piece number 1. Okay, so the good system is we want it to be as small as possible, the ARL values, ARL1. If RL0 here, we want it as large as possible. So if it can go beyond 370, meaning it is good. Okay, so but for control chart, okay, this is I'm referring to 370 here, referring to X bar chart. X bar chart has capability on average to provide 370 false alarm. Okay, at 370 as false alarm. Okay. So especially when we design control chart, okay, we use these measures to see whether the control chart that we design is good or not. Okay. This is what I was telling you. So if we have P equal to 0.0027, which is plus minus 3 sigma, 1 over P, which is probability, you get 370. Okay, for a stable process. Probability a single point falls outside limit when the process is in control. It is 370. Okay. So this is even the process remain in control, but an out of control signal will generate every 370. And the process is in control. Okay. So this is what I mentioned earlier. It is false alarm. Okay, this is false alarm. Okay. Okay, let's move on. Okay, I think the rest you can read on your own on this part. Okay, let me move on. Okay, how to determine how frequent we want to do the sampling. Okay, of course, large sample size is good. Okay, it is good to have a large sample size. Large sample size would allow shift to be detected, okay, twice as quick as the old one. Okay, so the bigger sample size, meaning the n values, the n we take. Okay, normally for X bar chart, the n will be 4 or 5. Let's say 5, we take it. But if we increase n to become 10, okay, so every time we take sample, we take sample. So this what I'm referring sample here is, you have a control chart. Okay, how many sample you take? Okay, we take as a general rules. As a general rule, you're going to take sample number 1 here, subgroup 1, subgroup 2, subgroup 3. Maybe subgroup 1 is at 8 in the morning. Subgroup number 2 is maybe 8:30. Subgroup number 3 is at 9 o'clock. Subgroup number 4 is at 9:30 and so on. Okay. So typically we take it about 25 subgroup. Okay, 25 subgroup. So if you take 30 subgroup, it will be better. But 20 is minimum, but some people just take in between 20 to 30, which is 25. Okay. So every time you take the sample, okay, we plot it. Let's say you plot here, sample number 1, subgroup number 1, subgroup number 2, maybe you take subgroup number 3, subgroup number 4. Okay. So this every subgroup, okay, we call it n n equal to 5, this is subgroup size. Subgroup size. Okay, so this value, the one that we cross here, actually representing a subgroup. Okay, a subgroup. So maybe this we can call it x bar 1, for example. So the average of 5 value. So x bar 1 is actually the summation of x1, okay, x2, okay, x5. If n is equal to 5, divide by 5. Okay, divide by 5. So the value that you plot here is the average value, okay, average value. So to get this line in the middle here, this is x double bar, okay? So x double bar is the average of the subgroup, okay? So you're going to have, let's say in this case is 25. Okay, so we divide this 25. Okay, this is what you get in this line. Okay, so related to this topic, it says that what is the sample size? So the question, the statement here say that the larger sample size, if we take 5 or if we take n equal to 10, okay, so if we take n equal to 10, okay, we will have double or we call it twice as quick as the old one. So the larger size, we have the chances to detect the shift faster, okay, because more accuracy when we have larger sample size. Okay, subgroup size. The subgroup G is subgroup. G is equal to 25. Okay, this is number of subgroup. How many number of subgroup? Okay, so the statement here is comparing if you use n equal to 5 or n equal to 10. Example here, maybe sampling frequency every half hour. Sampling frequency here is every hour because we take it every 5 here, half an hour. Here is we take 10, but we take it every hour. Okay. So this is when we design control chart, we have a choice. What should be the n value? What should be the g value? What should be control limit? So this is what we call it designing the control chart. Okay. We need also to understand, okay, how should we take the sample? Okay, related to what we call it rational subgrouping. Okay, rational subgroup. There are two ways of collecting the subgrouping, because our focus here is we want to detect the differences between subgroup or within subgroup. Okay, between subgroup or within subgroup. Yeah, I will show you a diagram. Maybe that will be clearer for you. If you look at this graph, here we have graph A and graph, I think this one should be B. This should be, actually what is showing is two different approach of collecting data. Okay, two different approach of collecting data. So the one on the left, this is, we call it instantaneous, okay, instant time period. Okay, instant time period. So this is, let's say, at that particular time, let's say this is 8 a.m. exactly at 8 a.m. we take five points. Whatever we have in the production that time, we take all the 5. Compared to the one on the right, so we are collecting example from 8 to 8:30. Okay, so this is period of time. Okay? During this period, anything produced between 8 until 8:30. Okay, during this period, we take sample. Okay, we take sample. So this is what we call it. How we select the rational subgrouping. So the effect is the sensitivity of the process mean. This is process mean. Okay, this graph is X bar chart is on the mean, and this one on the range, which is on the dispersion. This is on dispersion showing on the R chart. Okay, this is range. Okay, I will discuss more on this, how to prepare the control chart. But the point here is the method of collecting data play a role. Okay, either you collect instant time period, or you can collect a period of time. There is a period between certain duration. Okay, this one is instantly, whatever produced that particular time, you produce it. So we see here, okay, if we take a method like this, instant period of time, the variation for range is very little. Okay, range, but the variation, okay, for the mean, okay, you can see that more sensitive here, the mean. Okay, the mean is more sensitive compared to this one. This one mean is not so sensitive, but R is sensitive. Okay, this is low variation if we select like this, but if we select this way, duration of period of time, okay, R chart has more sensitivity. Okay, bigger variation here. Okay, but the mean, okay, the mean is less sensitive compared to this one. This one is more sensitive. Okay, so method of collecting data is very important. It play a role and affect our decision making for process monitoring. Okay, okay, there are also pattern on the control chart. Okay, I will discuss later on this. Let us go to how to prepare a control chart. Okay, when we prepare control chart, there are 2 phases. There are 2 phases of preparing control chart. Here we have phase 1 and we have phase 2. Okay, phase 1 is, we call it trial control chart, or the control limit will be trial control limit. Phase 2 is the control chart that we use for monitoring. Okay, so phase 1 in control chart is normally we call it trial control chart. Okay, where the process is at the beginning of the process, normally we use a trial. Okay, trial control chart, and we revise. Okay, we will involve revise. Okay, when we go to phase 2, this is the real control chart that we use for monitoring. Okay, there are 2 phases in preparing control chart. Phase 2. Okay, so phase 2 is for monitoring. So we monitor the future process based on phase 2 control chart. Okay, remember there are two stages in preparing control chart. So phase 1, normally the process is unstable. Okay, so the process may have some problem, some error, so we are keep adjusting. Okay, where we need to revise. Okay, so we need to remove assignable costs and revise the control chart. Okay, which in phase 2. Phase 2 we also call revise. Okay, we revise control chart. Okay, phase one, we call it trial control chart. Okay, if you have any question, okay, please ask. Otherwise, I just continue. Okay, I've shown you this. All right, any question before I move on? Okay. No, all right. Okay, let me just testing here. Okay, Mr. Aaron. Okay, what is different between trial control chart and revised control chart? Aaron? Abdul Rahman. What is the difference between trial and revised? Okay, no answer. Okay, let me try one more. Faiz? Also no answer. Okay, anyone, please. What is the difference between trial control chart and revised control chart? I just explained just now.
The trial control chart is at the phase one, which is trial where we have trial control limits, and the revised control chart is to monitor the real one, which is at phase two.
Okay, so normally why we need to do trial?
To remove the assignable cost.
Okay, to remove assignable cost. Normally at the beginning of a process, the process will not be stable. Okay, because it's a new process. The beginning of process, normally we say we are preparing a trial control chart. Once we understand better about the process, okay, we remove assignable cost, which is a cost that causing the process to become unstable. Unstable here meaning that there will be some point will be outside control limit, okay, due to instability, okay, due to be variability in material, variability in operator skill, variability in maybe there is some disturbance in the process, okay, maybe vibration, too much vibration. Vibration can be coming from the foundation of machine, okay, the flooring, maybe the building itself create vibration. Okay, so after we remove all the source of vibration by improving the setting up the machine, by improving the workers' skill, we can remove those variability and we have to revise again the control chart. Okay, the revised control chart is where we remove assignable cost. We call it phase two, where this is where we use for monitoring, or we can use it for controlling the future process. Right, so in control chart, the common control chart is we call it short control chart. Short control chart. So where we have the center line, which is mu here, which is the mean, and mu W, so this is the mean, basically is the mean. So in a simple way, normally we say that upper control limit will be equal to X double bar. We use X double bar because it's from sample. Mu is actually from population. X double bar plus 3 sigma X bar. Okay, so this is they are putting L here, but normally we use L equal to 3. Okay, so for lower control limit, okay, we have X double bar, okay, minus 3 sigma X bar. Okay, so this is what we call it based on short control chart. Okay, so however this I've explained how to get X bar. So there is also simplification of this control chart. sometimes people refer this, they're using values from table. Okay, we replace 3 sigma X bar with A2 R bar. Okay, what is R? R is range. R means maximum value minus minimum value for that subgroup. Okay, so R bar is the average of, okay, R bar is the average of the R value. Okay, so the R bar will be, so we have so many R. We have, if we have 25, so we have R1 plus R2. Okay, until let's say 25, you're going to have R25. Okay, divide by 25. Okay, in the past, there was no calculator to calculate the standard deviation sigma. So people prefer to just simple mathematics. They just collect what is the maximum value and what is minimum value for each subgroup. They got it R, okay, 25 sample, 25 R, and then get R bar. And then to get upper control limit for X bar chart, they just plug in into this formula, okay? So for the lower values, it's the same. The lower control limit, X double bar minus A2 R bar. Okay, so where do you get A2? A2 is coming from table. Okay, A2 is a factor in the table. Okay, is a factor, it's from table. So we select the value A2 based on sample size. Okay, what we call it a factor table. Okay, we will provide a factor table. So depend on n. Okay, different n will have different A2 value. Okay, depend on n. If n equal to 4, different value, then n equal to 5. Okay, normally we use n equal to 4 or 5. Okay, n is the subgroup size, or sometimes it's known also as a sample size. Okay. All right, so there is a difference between if you take individual values, okay, if you plot individual values compared to when you plot X bar values. X bar value, you're going to have a smaller range for the upper control limit and lower control limit. Okay, that's why we normally plot X bar chart compared to we plot X chart. If we plot individual value as X chart, you're going to have this distribution, very large variability. Okay, so the value might be somewhere here, the upper control limit. Okay, so in control charting we use X bar chart, okay, which is smaller range because we already eliminate, okay, random variation by taking the average. Average is actually a filter. It's like a filter. If you study electronics, it's like a filter. But here the filter is we are taking the averages. We average and remove random variation by taking average. Okay, let me just finish up this one. Okay. Okay, when we say control chart design, we are referring to selection of sample size, selection of control limit, and selection of sampling frequency. Okay, So we are designing what? We don't design product here, but we design control chart. Okay, designing control chart. Why determine what is sample size, what is the control limit, and how you want to select the sample. Is it you're going to select at fixed interval, or you're going to select throughout the period? Okay, as I mentioned earlier, it could be instant time period where you are taking at that particular instant, you take all the product produced at that particular time. Or another way, starting from 8 to 8:30, for example, anything that is produced in that duration, you will select the sample. Okay, you will select the sample. Maybe if you need 5 only, so anything in between, you select this one, you select this one, select this, okay, and maybe, you know, to make it enough. So this is another method of selecting. Or in this case, you are, the second case, you are producing, okay, maybe the machine produce a few items within that particular minutes, okay. So this one is as exaggerating. So if you select, okay, I want to select at this point, so all that produce that instant of time, you select it, okay, for the purpose of preparing control chart. There is a difference. The sensitivity of chart will be different if select like this or select like this. So this is our concern of sampling frequency. Okay, how we want to select the sample. Okay. Okay, there is sensitizing rule. Please read this synthesizing rule. I will discuss in that class. Please read before the class what we call also Western electric rules, how we can interpret variation within the control limits. That is some basic of the control chart. Okay. I will select one problem for you to try to use this basic formula for X bar chart. Okay, I will put it in your e-learning. Okay, you need to exercise how to prepare X bar chart. Okay, and also this note I will upload to e-learning after this. All right, any question?
Doctor, when will be our test one?
Okay, your test one will be week number 6. This is week number 4. Okay, next week, week number 5. After that, we're going to have test number 1. Okay, so the coverage will be up to whatever I discuss until next week. Okay, including this, what we discussed today on the control chart. Right?
Okay, doctor.
All right, any more question? Okay, before we finish, okay, okay, let me check here. Okay, I think that's all for today. So, okay, thank you very much. So I see you again next week. So don't forget, I will put a question for you to solve using this X bar chart. Okay. There is no question. That's all for today. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doctor.
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 Thank you, semua.
Thank you, doctor.